Yeah, I guess we can get started for one. Okay, so yeah, let me start. So, okay, hi everyone. Welcome to the KAIST SoC Colloquium. This is our second time to have the talk in this first semester. I'm Min Hyuk-sung at KAIST. And today I'm very happy to introduce our very special speaker, Michael Bronstein. And thank you for joining talk at the early morning in London, which might be 8 a.m. there, right? Yeah, thank you. So Michael Bronstein is a professor at Imperial College London, where he also holds the chair in the machine learning and the pattern recognition. And also Michael is the head of the graph learning research at Twitter as well. And he's also leading the machine learning research in a project called CETI, which is a kind of interdisciplinary research initiative that has been also awarded the TED Audacious Project Prize. Especially his project is like understanding the communication of the sperm whales. So quite interesting. And Mike also received his PhD from the Technion in 2007. And after that, he has been a visiting researcher at Stanford, MIT, and the Harvard, and also has affiliated with many places, including TUM, Technical University of Munich, as a Rudolf Diesel Fellow, and also at Harvard as a Radcliffe Fellow, and also at Princeton as a short-term scholar. And Michael also has won many awards. He is the recipient of the Royal Society Upson Research Merit Award, Royal Academy of the Engineering Silver Medal, and also 5 ERC grants, and also 2 Google Faculty Research Awards, and also 2 Amazon AWS Annual Research Awards. And he's also a member of the Academia Europaea and a fellow of the IEEE, IAPR, BSc, and also ALICE. And he's also a ACM Distinguished Speaker and the World Economic Forum, the Young Scientist. And also not only in the academia, but also in the industry, Michael is a serial entrepreneur and founder of the multiple startup companies, including the Novafora and the InVision, which is acquired by Intel in 2012, and VideoCities, and also Fabula AI, which is also acquired by Twitter in 2019. And he also has been a principal engineer at Intel, the perceptual computing, and also was one of the key developers of the Intel RealSense technology. So please join me in welcoming Michael Bronstein, and Michael will talk about the geometric deep learning from the Euclid to the drug design. So while we, so one more thing is that while we switch the screen shares, let me stop my screen sharing. Oh, so let me start the recording. Sorry, just 1 second. I'd like to start the recording. Okay, now the talk is recorded. And one more thing is that now our talk is also live streamed through our YouTube channel. So thank you, Michael, for allowing us to live stream the talk as well. The thing is that we close the chat in the YouTube streaming to basically make it easier to have the Q&A session after the talk. So if you have any questions, please join the Zoom meeting and also leave the questions in the Zoom chat. Then I will basically collect all the questions and ask them after the talk.
Thank you very much. Thank you. I would like to thank the organizers for this invitation. So really great. Unfortunately, though through Zoom, I wish I could come in person, but I guess that's the current reality. So thank you very much for this kind introduction. And today I would like to talk about what we call geometric deep learning. So some of you might have seen a version of this talk at ICLEAR earlier this year. So it is based on a book we are currently writing with my colleagues, Joan Bruna, Taco Cohen, and Petr Viličković, that is titled exactly this, geometric deep learning. And I would like to maybe open a little parenthesis and take you back in history to try to motivate basically what geometric deep learning is and why we need geometry in order to do deep learning nowadays. And just one comment that you can also find some more materials on this website, where we also have recording of an entire course that we gave over the summer on this topic. So if we go back in history to the origins of geometry, which probably can be traced back to at least the ancient Greece, the only geometry that we knew for more than 2000 years is what we nowadays call Euclidean geometry, and no other geometry really existed. And the situation changed quite dramatically in the 19th century. So there has been a cumulative set of results that basically came from the impossibility to prove what is called the fifth postulate of Euclidean geometry about parallel lines. So actually precursors of these were already the construction of what is called the projective geometry. Poncelet essentially rediscovered it in the beginning of the 19th century, but probably the first constructions of what we nowadays call non-Euclidean geometries are due to Lobachevsky, Bolyai, even Gauss himself, even though he never published, and then his PhD student Bernard Riemann. So they constructed examples of different kinds of geometry, and towards the later part of the century, what happened is that there was an entire zoo of different geometries, and it was more a philosophical question, which geometry is the right one, and actually how you define in geometry, how all these different geometries are related to each other. So, and this created a somewhat unhealthy situation. It was not clear how these fields are related, and the solution came from a young mathematician called Felix Klein. So he was German, and got an appointment as a full professor at the age of 23 at a small university in Bavaria in the town of Erlangen. And he was asked, as it was customary in Germany, to present his inaugural research program that entered the history of mathematics as the Erlangen Programme. And in this program, Klein proposed a very radical approach or change of mindset in studying geometry. And he suggested that you need to treat geometry as the study of invariants or symmetries. So these are properties that would remain unchanged under some class of transformations. So, for example, you could say that rigid motions, right, rotations, translations, and reflections preserve properties such as distances, angles, areas. So you can derive the Euclidean geometry from rigid transformations. And if you relax a little bit the assumption, you can allow, for example, for a fine transformation, you get the fine geometry. And if you relax it even further, then you have projective geometry. And he used the language of group theory to formalize these notions of transformations. And these ideas appear to be very powerful. So you can, for example, say that the category theory is a direct continuation of these ideas of the Erlangen Programme. But the impact of these ideas also spilled into other fields, in particular into physics, where it was shown by Emmy Noether that you can use symmetry considerations to derive conservation laws from first principles. So you can prove that energy is conserved in a physical system by assuming the symmetry of time, for example, which is extremely powerful because previously conservation laws were purely empirical. And these ideas took further evolution. So through the notion of what Hermann Weyl initially called gauge invariants, and in certain generalized form with non-abelian groups, that was done by Young and Mills in the 50s. Basically, it proved successful in providing a unified framework to study the fundamental forces of nature, with maybe the exception of gravity. So in the 70s, it was called the Standard Model, and it describes, again, gravity doesn't fit into this picture, but otherwise, it's all the physics that we currently know. So I can quote here another physics Nobelist, Philip Anderson, that we can say with only slightly overstatement that physics is the study of symmetry. Now, you may wonder, I can close this parenthesis here, and you may wonder at this point, what does it all have to do with deep learning, right? And why am I telling you this? So first of all, I think the situation that we see nowadays in deep learning is very similar to what happened in geometry in the 19th century. So we have, of course, deep learning is now a very popular approach, and I think it is, without exaggeration, it has made a revolution in data science and allowed to solve tasks that maybe 10 years ago would be considered impossible, whether it's computer vision, speech recognition, natural language translation, playing intelligent games, folding proteins. On the other hand, it created an entire zoo of different neural network architectures that are suitable for different kinds of data. But there are very few underlying unifying principles. And as a result, it is difficult to understand how different methods are related, same as we had in geometry in the 19th century. And inevitably, it leads to reinvention and rebranding of the same ideas and the same concepts, and it is also a somewhat unhealthy situation. So what we are trying to do in geometric deep learning is using the spirit of the Erlangen Programme for some form of geometric unification of deep learning. And there are two purposes for this program. First, to provide a common mathematical framework from which we can derive from first principles some of the most popular and successful neural network architectures. So you can think of this as a kind of pedagogical approach. And second, you may wonder what will be there after deep learning, right? Because deep learning is, even though it's new, not new, but we might go at some point beyond, let's say, backpropagation based learning methods. And we hope that these principles are more powerful than their specific incarnation with current deep learning architecture. So it is an overarching principle that will allow possibly to build machine learning architectures in the future. So the term itself, we popularized it in the paper that we published in 2017 in the IEEE Signal Processing magazine. And today, geometric deep learning is used almost synonymously with graph neural networks, which is one of the particular instances of this framework. But I hope to show you today that it's a much broader picture. So allow me to start with looking at maybe the simplest instance of machine learning, which is supervised learning. And we can essentially consider it as a function estimation problem. So where given the outputs of some unknown function, right, that is shown by a black box here, that we can evaluate on a training set. So let's say that we want to classify cats and dogs. So we know the labels of a few images of cats and dogs. So what we try to do is to find a function from some hypothesis class that fits well the training data. And it would allow us to predict the outputs on previously unseen test inputs. So what happened in the past decade and why deep learning became so prominent is that two trends coincided. So first, the availability of large and high quality labeled data sets, such as ImageNet, which contains millions of annotated images. And second is the computational power, in particular, the possibility to use GPUs to design rich function classes that have the capacity to, at least in principle, to interpolate such large data sets as ImageNet. And neural networks, even though they're not new at all, they're probably more than 70 years old, appear to be a suitable choice to represent general functions, because even with a very simple choice of architecture, such as perceptron that I show here, we can produce a dense class of functions. So if I just have a two-layer perceptron-like neural network, I can approximate any continuous function to any desired accuracy. So this is a property that we call universal approximation. Now, the setting of this problem is a classical problem in approximation theory, and it has been studied very extensively over the past at least 100 years. We have very accurate results and bounds on the estimation error. So essentially, I can tell you how I need to sample my function in order to produce approximation of certain quality. But these results do not hold in high dimensions. And what happens in high dimensions, and this is essentially how machine learning problems look like, even if we take a very simple regular class of functions, let's say Lipschitz continuous functions, and the example that I show here that we also study in the book is a superposition of Gaussian blobs that are put in different quadrants of a unit cube. So when we grow the dimension of this unit cube, you see that the number of samples need to grow very fast with the dimension in order to guarantee certain error. And in fact, it grows exponentially. So we get a phenomenon that is colloquially known as the curse of dimensionality. And again, in machine learning, we don't deal with functions in 2 dimensions or even in 10 dimensions or even in 100 dimensions. How about thousands of dimensions or even millions of dimensions? So this curse of dimensionality is always there. It is always built in and baked into most modern machine learning problems. So this naive approach to learning is really impossible. Now, this is probably most prominently seen in computer vision problems like image classification. So even the very small images tend to be very high dimensional. So this is m-nis digit. It's 32 by 32 pixel image. This is almost 1,000 dimensional vector. So what we typically do with this kind of data, we parse them into vectors and we can feed them into into, let's say, the perceptron. But we see intuitively that a lot of structure is this way is broken and thrown away. And if, for example, I shift the image by just 1 pixel, I will see that this vectorized input will be very different. And as a result, we need to show a lot of different examples to the neural network in order to learn that shifted inputs must be classified in the same way, right? So we need to do what is called data augmentation. And the remedy in computer vision came from classical works in neuroscience that showed that there is certain organization in the neurons in the brain, in the visual cortex, into what is called local receptive fields. And this inspired a new class of neural architectures in the 80s, such as the neocognitron of Fukushima, and then convolutional neural networks, the classical work of Jan LeCun and co-authors, where weight sharing across the image effectively allowed to solve the problem of the curse of dimensionality. But we also have kind of data where we don't have this underlying grid structure like we have in images. So here is an example of a graph that represents a molecule. And let's say that we want to predict some properties, right, such as binding energy of this molecule, which is a classical problem in, for example, drug design. When you want to develop a new drug, you want to virtually analyze different molecule candidates, whether they will bind well to their target, right? And here the nodes represent atoms and the edges represent chemical bonds. And again, we can apply, we can vectorize the data in this graph and apply, let's say, a standard perceptron neural network to this input. But the problem we can already see here that we don't have a canonical organization or ordering of the nodes of the graph, unlike we had in images. And this is this will require a different kind of geometric assumptions. And molecules are just one example of these irregular non-Euclidean structured data. We have other examples from, for example, the domain of social networks or interaction networks in biological sciences or meshes in computer graphics and so on and so forth. So let's look again at this problem where we thought that it would be hopeless because of the curse of dimensionality, where we tried to take multidimensional input such as images and classify them. What happens in many machine learning problems is that we do have additional structure that comes from the underlying geometry of the input signal. And in particular, in images, this kind of geometry is the geometry of the grid. So in our example, the input image is not just a d-dimensional vector, but it's a signal that is defined on some domain, right? A two-dimensional grid. Now, we can capture the structure of this domain by describing its symmetry group. So in this case, it's a group of 2D translations that act on points in the domain. And in the space of signals, right, in the space of images, these group actions are manifested through what is called the group representation. So just to make things more concrete, in our case, this will be what is called the shift operator. We'll see it in a few minutes. And it can be represented as a D by D matrix that acts on this D-dimensional vector. Okay, so we can bake in this structure of the domain into the architecture by the way that it acts on the image. And one way of doing it is by assuming what happens to a function that is applied to this image. And we can have functions that are unaffected by the action of the group, what we call invariant functions. And if we want, for example, to recognize an object in an image, no matter where the object, right, let's say cat in this example, located in the image, we still want to say this is a cat, right? So it's an example of shift invariance. On the other hand, we can have a case where the function has the same input and output structure, like think of a problem of image segmentation. So the output will be a pixel-wise mask. And we want the output in this case to be transformed in exactly the same way as the input. And in this case, we say that the function is equivariant. And in this case, it's shift equivariance. Now, another geometric prior is what is called scale separation. And in many cases, we are able to construct a multi-scale hierarchy of domains by somehow assimilating nearby points and also producing a hierarchy of corresponding signal spaces that are related by what is called the coarse graining operator. And on these coarse scales, we can also apply coarse grained functions. And we are in particular interested in what is called locally stable functions that can be approximated as a composition of the coarse graining operator and the coarse scale function that I denote here by f prime. So, and you see that maybe symmetry is very prominent in physics, right? And we know that we can derive all physics from the notions of symmetry, but so is scale separation. So, it is actually one of the reasons why we can describe physical systems at a certain level of abstraction. So, for example, when I sit in this room, so there are probably quadrillions of molecules running and colliding with each other in the air. And yet I don't model each molecule separately, right? Because it will be computationally intractable. We have statistical mechanics that allows us to do it with small number of degrees of freedom. So if I zoom out, actually, I see the Earth, where we have the atmosphere and this movement of these quadrillions of molecules as a point that orbits the sun. And at this scale, I don't care about all the internal details and the maybe heterogeneous composition of the Earth. I can model it as a point because at the cosmic scale, it doesn't matter at all, right? So that's exactly the idea of separation of scales that we can also implement in machine learning. And so these two principles, symmetry and scale separation, give us a very general, generic blueprint of geometric deep learning that you can recognize in the majority of popular deep neural network architectures. So typically it comes as a sequence of equivariant layers, such as convolutional layers and CNNs, and then possibly applying a global pooling layer if we have, for example, image classification problem. And in some cases, we also have a hierarchy of domains that are created by some coarsening procedure that takes the form of local pooling in neural network architectures. And this is a very general design we can apply to different types of geometric structures, such as grids, maybe more general homogeneous spaces with global transformation groups, graphs, manifolds, and so on. So this is what we call the 5G of geometric deep learning. And we can see that the implementation of these principles, as I hope to show you today as well, leads to some of the most popular neural network architectures, whether it's CNNs, GNNs, deep sets, transformers, and so on and so forth. So let me maybe start with graphs. Graphs are, as you know, a very common way of abstracting data that describes relations and interactions. And probably a good metaphor for graphs is a social network where we have users that can interact with each other. So the users are the nodes of the graph, and their interactions can be modeled as edges. And we can also attach some features to the nodes that we model as d-dimensional vectors. Okay, so that will be our model of attributed graph that we have node attributes. So one key structural characteristic of graphs is that actually graphs are abstract topological objects. So when I take, for example, the matrix, the feature vectors attached to each node and arrange them into a matrix, I prescribe some ordering of the nodes. That is purely arbitrary, right? And so I can also, this is convenient because I can also model the structure of the graph using the adjacency matrix. So it's a matrix where I have a 1 in the position ij if there is an edge between node I and j, and 0 elsewhere, right? So by changing the order of the nodes, I will get a different arrangement in the feature matrix, and so also in the adjacency matrix. So this can be described by the permutation, which is actually the natural symmetry of graphs and sets. And you can think of the permutation matrix P as the representation, right? What we called the row before of this symmetry group. And if we want to compute functions on the graph, for example, if we want to compute the energy of a molecule, that we use in the example, in this case, I don't want to be sensitive to the way that I rearrange the nodes of the graph. So in other words, we want to have a permutation invariant function. If on the other hand, I want to do maybe node-wise predictions on the graph, for example, in social network, I would like to detect maybe some maliciously acting users. I want, in this case, the output to be permuted in the same way as the input. So I want the permutation equivariant function. And it appears that the most generic way of computing such functions is not computationally tractable because our group is too large. But what is typically done is you consider local functions that just look at the neighbors, so nodes that are attached by an edge to some node I, and you aggregate the information from these neighbors and do some computation using this local neighborhood at every node of the graph. So specifically, we take what is called the multiset of the neighbor features. Why it's a multiset? Because the same feature vector can appear more than once. So a multiset is a set where the element is repeated more than once, together with the features of the node itself. And we aggregate them by some function that I denote by phi. And I remind you that we don't have a canonical ordering of the nodes in the graph, so the neighbors can be arranged in any way I want. That's why this function must be permutation invariant. Now, if I apply this function at every node of the graph, it is easy to show that actually the result will be a permutation equivariant function. So locally, permutation invariant function applied at every node of the graph gives a permutation equivariant function. And actually it appears that the choice of this aggregation, the function phi, is crucial. And in some cases, when this phi is injective, we can relate it to what is called the Weisfreier-Lemon graph isomorphism test. It's a classical algorithm in graph theory that tries to determine if two graphs are isomorphic. So we say that graphs are isomorphic if one can be permuted into another, or in other words, there is an edge-preserving bijection between them, right? So in a sense, these graphs are equal up to the labeling of their, or the ordering of their nodes. And what Weisfreier-Lemon algorithm tries to do is tries to color the graph using the structure of its neighborhood. So by color, I mean a discrete label. So it starts with, let's say, a graph where all the nodes are blue, and now we have two types of neighborhoods, right? So we have a neighborhood that has three neighbors, and a node that has two neighbors. So these will be hashed by an injective function into two different colors. Let's call them yellow and green. And now we can repeat the procedure once more, and now we have three types of neighborhoods. So we have a green node with two yellow neighbors. We have a yellow node with one yellow and two green neighbors. And we have a green node with a yellow and a green neighbors. So these will become violet, red, and gray. But if I repeat this procedure again, the colors are stopped changing. So now we can output the distribution of these colors. And if I give you another graph, we can repeat the same procedure, and I see that the colors are different. The distribution of colors is different. We know for sure that the graphs are not isomorphic. But if the colors are the same, we actually don't know. So they might be isomorphic. And this is, in other words, a necessary but insufficient conditions for isomorphism. And in fact, we can find examples of graphs that are deemed equivalent by the Weisfreier-Lemon test, but they are not isomorphic. And the example that is shown here, the graph on the right has triangles, the graph on the left doesn't. And this simple approach cannot even detect triangles, cannot count triangles in graphs. But it's still quite powerful algorithm. And the typical way that local aggregation functions look like in graph neural networks is, first we have some permutation invariant aggregation operator, such as sum or maximum. And again, the choice is important. Sum is injective, for example, maximum is not. We have a learnable function psi that transforms the neighbor features, and another function phi that updates the features of node I using the aggregated features of the neighbors. And there is a lot of nuances on how to design each of these components. And fortunately, most of the architectures that exist in the literature can fall into one of the following three flavors. So the first flavor is convolutional. And in this setting, we aggregate neighbor features that are weighted by some fixed coefficients that depend only on the structure of the graph. And this can be interpreted as a kind of importance of node J to the representation of node I. And we'll see that this scheme on grids boils down to the classical convolution. The second flavor is based on attention, where the aggregation coefficients depend also on the features. And in the most general case, we have a nonlinear function that depends on both feature vectors of node I and J. And the output of this function can be regarded as a message that is sent to update the features of I from J. And these are the message passing graph neural networks. So if you look at a typical graph neural network architecture, I hope you can immediately recognize an instance of our geometric deep learning blueprint, where we have the permutation group as the geometric prior, and we have a sequence of permutation equivariant layers that do this propagation on the graph. We also have an optional global pooling layer that produces a single graph-wise output, and possibly some local pooling layers that are obtained by graph coarsening that can also be learnable. Now, let me show you some interesting corner cases or special cases of graph neural networks, and one of them is a graph with empty edge set. So this is just a set. We have only the nodes. So a set is also unordered, same way as a graph. And in this case, we can do two things. So in the most straightforward approach would be to treat each element of the set entirely independently. We apply a shared function phi to their feature vectors. And in this case, we get a permutation equivariant function over the set, which is a special setting of a graph neural network. And this is what is called deep sets or point nets in machine learning architectures. A second approach would be to assume that every node or every element in this set can interact with any other element. In this case, we have a complete or a fully connected graph. And on this fully connected graph, actually, the convolutional flavor makes no sense because the aggregation will be over all the set of nodes. So the second argument of this function will be redundant. So we need to use at least the attentional flavor. And we can interpret the attention as a kind of learnable soft adjacency matrix. And I hope you can recognize in this instance of graph neural network the famous transformer architecture that is now ubiquitous in NLP applications. So I should say that transformers are typically applied to sequence data where we actually do have some prescribed order of the nodes, right? Like a sequence of words in a sentence. And typically this node information is provided in the form of what is called positional encoding. So these are additional features that uniquely identify the node and allow to adapt locally the message passing mechanism to the position in the graph. So in graphs, in more general graphs, we can also use positional encoding or structural encoding. There are multiple ways of doing it. One way of doing that we showed in a paper with my students, Yorgos Bouritsas and Fabrizia Frasca, is counting small graph substructures such as triangles, cliques, or cycles. And this way we provide a structural encoding that can be shown to be not less powerful than the Weisfreier-Lehmann test, or actually in some cases strictly more powerful than the Weisfreier-Lehmann test by appropriate choice of this substructure. And you can consider it as a kind of problem-specific inductive bias. So for example, in organic chemistry, a prominent structure are cycles. So you can see here again the same molecule of caffeine that I showed in the beginning. It has a 5 cycle and a 6 cycle. So for example, aromatic rings are 6 cycles. So if we count the cycles of this size, what we observe in experiments is that our ability to predict chemical properties of molecules, in this case, for example, the solubility property, improves dramatically if we incorporate these extra structures. So you can see that even in cases where the graph is not given as input, such as a set, graph neural networks still make sense. But what happens recently in this field is that even when the graph is given, there is the trend of decoupling the computational graph from the input graph, right? So you would do message passing on some other graph that is not necessarily the same as the graph that is provided to you. There is a variety of reasons to do it, such as information bottlenecks, as well as multiple ways of doing it, and it can take the form of, for example, graph sampling, typically to address scalability issues, rewiring the graph. So there are multiple ways trying to change the connectivity of the graph, for example, to alleviate these bottlenecks, or maybe using larger filters that look at multiple hops, not necessarily the immediately adjacent neighbors. It is also possible to learn the graph, and it can be optimized for the downstream task and also changed in the layers of the graph neural network. And one of the first architectures to do this was what we call dynamic graph CNNs. So this was a collaboration with my colleagues from MIT. And maybe in historical perspective, this kind of latent graph learning can be related to nonlinear dimensionality reduction and manifold learning, where the key premise is that even though your data is very high dimensional, it has somehow low intrinsic dimensionality that can be at least metaphorically captured by assuming that the data is sampled from some low dimensional manifold, like this Swiss roll surface that is a 2-dimensional manifold in R3. And the typical way that these algorithms would proceed is to first represent this manifold structure by some k-nearest neighbor graph, then embed this manifold in a low dimensional space where it would be easier to do some machine learning tasks such as data clustering. And one of the reasons why these methods struggled and really never became used in, let's say, production machine learning system is that these 3 steps are completely separate from each other. And you can obviously see that the way that I build, for example, this initial graph will affect hugely the way that it is embedded and the way that the clustering will look like, right? So with modern deep learning pipelines, and that's why I call it manifold learning 2.0, we now have a way to build an end-to-end pipeline where we build the graph and the filters on this graph in the form of graph neural network with latent graph structure. And some of the recent applications of these ideas, an architecture that we call differentiable graph module, or DGM, that we developed with colleagues from TUM in Munich. We use it for automated diagnosis application of neurological diseases, and we can show that we can consistently outperform graph neural networks with handcrafted graphs that come from, for example, some population features. So let me move to another geometric object, which is a particular instance of a graph, and this is a grid. So a grid is obviously a kind of a graph, right? So here is what is called the ring graph. So it's a grid with periodic boundary conditions. And what we immediately observe on the grid is that we have a fixed neighborhood structure. So every node has exactly 2 neighbors. And not only that, we also have a particular order. So I remind you that on graphs, we're forced to use a permutation invariant local aggregation function phi, right, that acted on this multi-set of neighbor features because we didn't have a canonical ordering of the neighbors. On a grid, we actually do, right? So we have the ordering of, let's say, green, red, and then blue. So this function can be made more specific. And if in particular we make this function a linear aggregation, we get the classical convolution that in matrix vector form can be represented as a special matrix that is called a circulant matrix, right? So that's exactly the weight sharing idea that I mentioned in the beginning in convolutional networks. This matrix is created as shifted copies of a single vector of parameters that I denote here by theta, one column of this matrix. And what characterizes circulant matrices is that they commute with respect to multiplication. And in particular, they commute with one special circulant matrix that cyclically shifts the position of a vector by one element, what we call the shift operator. Remember, in the first example, I promised you to show the shift operator, so here is the shift operator. So circulant matrices commute with shift, which is just another way of saying that convolution is shift equivariant, right? I can first apply convolution, then shift, or vice versa, the result will be the same. So in signal processing literature, for some reason, this is often called as shift invariance. So purely mathematically speaking, the correct term is shift equivariance. Now, what happens also is that this statement works in both directions. Not only every circulant matrix commutes with shift, but also every matrix that commutes with shift must be circulant. So what we get is that convolution is the only linear operation that is shift equivariant. And you can see here the power of our geometric approach that we can, basically what we get here is that convolution automatically emerges from the assumption of translational symmetry that we assumed here. And I think this is very nice, very beautiful, and very powerful that we can derive such architectures as CNNs from first principles. So it just doesn't come out as a formula out of the blue. You can also derive the Fourier transform. Basically, this will be what is called the irreducible representation, or you can use the property of commuting matrices being jointly diagonalized. So this will be the joint eigenbasis in which all convolutions become diagonal matrices. And then we get this duality between the Fourier transform, or doing the convolution in the Fourier domain as pointwise product of Fourier transforms, or the equivalent spatial domain conversion as a circuit matrix. Now, let me move to a more general case where our group formalism will become more prominent. And again, we can think of convolution as this kind of pattern matching operator, right? So what circulant matrix does is it applies the same weights at every position of the signal. So in case of an image, we can think of it as a kind of pattern matching operation. So we extract a page of pixels, multiply it by a mask, and then we move to a new position. So let me formalize it a little bit more. So we can define it by defining a shift operator, right, that I denote here by T, a filter that I denote by psi, right, and an inner product that matches the filter to the image. So what convolution does is I move around the filter, around the domain, and I match it to the image, right, or to my signal. And if I do it for every shift, I get the convolution. Now, this is still a very special case because here the translation group can actually be identified with the domain itself, right? Again, these are completely different structures. So a group is defined only by the way that its elements are composed, but still we can represent the shift operator by a point to which we shift, which is an element of the domain omega, element of the grid, right? And this is not the general case. And in general, we'll have the filter transformed by the representation of our symmetry group that they denote by rho. And the convolution now will have values for every element of the group G. So the important thing to understand is that the symmetry group is completely detached from the domain. And it is to a large extent application dependent. So even if our signals are images in the plane, we can assume typically the translation group, but we can also assume the rotation group, right? It depends on the application. So if you, let's say you want to do traffic sign recognition in a self-driving car, so most likely you will not get a tilted version of the signs, right? So translation in this case makes a lot of sense. If, for example, I have a flying car, I don't know, futuristic self-driving airplane, of course I can also tilt the images. So in this case, I want a rotor translation group. If, for example, I still don't have reflections because they are not physical, but if you think of another application like a classifying, for example, histological samples where I want to detect cancer, this is a slice of tissue that I put under a microscope. In this case, I can have both translations, rotations, and also reflections because I can flip the sample glass, right? So it really depends on the application, what kind of symmetry I need to assume. So this thing complicates a lot. The fact that the structure of the group is different from the domain makes things different from what we have in case of translation group. And here's an example of how to do convolution on the sphere. And in this case, the domain is a two-dimensional sphere. So it's a manifold. It's what is called S2. And the group that we assume here is the special orthogonal group SO3. So it's rotations that preserve orientation. And we can think of points on the sphere as three-dimensional vectors of unit length. And the elements of the group can be represented by orthogonal matrices R with determinant equal to 1, right? Determinant equal to 1 means that I preserve the orientation. So the convolution here is defined on SO3. We get the value of inner product for every rotation of the filter. And if I now want to do the convolution on the output signal, right, another layer of convolutional network, now the domain will be SO3 itself. So points on this domain will be matrices, will be rotations. So it's a three-dimensional manifold. SO3 is a three-dimensional manifold. It's a Lie group that has a three-dimensional manifold structure. So unlike the case of two-dimensional convolutions, where the input and the output have exactly the same structure. Okay. Now, and even though the sphere is an example of a non-Euclidean space, a manifold, it is still quite special. So every point on the sphere can be transformed into another point by an element of the symmetry group of rotations. So in a sense, there is complete democracy among the points. And we call such spaces homogeneous. And in this case, we say that the group acts transitively, or in other words, we have some global symmetry structure. But this is not the case on general manifolds. And on general manifolds, we don't have a way of moving one point to another point, right? Or moving our filter around by a group element. So we need some more intricate and nuanced construction. And one way of seeing is that if I take this sliding window idea, right? So if I want to move my filter around an image, it doesn't matter which way I go, right? I can go along the blue path or along the green path, I will arrive at the same result. The situation is dramatically different on a manifold. So on the manifold, if I go along the green path, or if I go along the blue path, I will arrive at a different result. And this is what is called parallel transport in differential geometry. And what it says is that as a result of moving, a vector also rotates. It depends on the curvature, what is called a connection that changes the vector. And the result of moving a vector is path dependent. So let me maybe first give you a crash course on differential geometry. What are manifolds, right? Because they are a little bit exotic objects, maybe in this domain of machine learning. So a manifold essentially is locally Euclidean space. What do I mean by locally Euclidean? It means that I can take a small neighborhood of a point map it locally to Euclidean space, what is called the tangent space. And the tangent space can be equipped with additional structure, because a manifold on its own is just a topological space. Roughly speaking, we have the notion of proximity or a neighborhood, but not the notion of distance. So to measure distances or angles or areas, we need to define what's called a Riemannian metric. So it's an inner product at every point in this tangent space. And if I deform the manifold without affecting the metric, I say that it's an isometry, right, or a metric preserving deformation. And isometry is also, not surprisingly, form a group. So we can define an analogy of convolution by applying these local filters in tangent spaces. And if we make this construction express entirely in terms of the Riemannian metric, what is called intrinsic, then we get deformation invariants baked into this architecture, right? So we'll be invariant to the isometry group of the manifold. And in fact, the first architectures that we developed in this in my group for deep learning on manifolds and meshes, what we call geodesic CNNs, were the first instance of such invariants. Now, what is important to say that actually what I write here is a cheating, because I don't really have a way to write this expression. When we work locally on a manifold, we don't have a global system of coordinates. So we need to fix a local frame at each point, or what is called the gauge. So remember the gauges or gauge invariants from the beginning. This is what physicists call gauges. So it's just a fancy name for prescribing a local reference at every point of the manifold, right? So I equip each tangent space with its basis of coordinates with respect to which I can express vectors, right? And with now this the definition of these bases is not unique. So we can apply what is called a gauge transformation that can transform these bases more or less arbitrarily. Now, what is this transformation, or what is called the structure group of the manifold, depends on what kind of structure you assume. So if it's a general manifold, just a topological space naked without any additional structures, then this can be a general linear group. I can transform the system of coordinates in any way. If I have, for example, a volume form, I can talk about orthogonal transformations that preserve volumes, right? If I have a Riemannian metric, I can preserve orientation, and I can preserve volumes. So we are talking about special orthogonal group, right? In the case of surfaces, two-dimensional manifolds, basically this ambiguity amounts to rotation of the local frame in the tangent space. And if we make the filter transform in the same way as I transform the system of coordinates, I get what is called gauge equivariant filters. And a beautiful line of works by my collaborator Taco Coin showed how to design such convolution-like or generalization of convolutional networks to this general setting. And why this is important, why at all we care about manifolds, is that in computer vision and graphics, two-dimensional manifolds or the discretization meshes are a standard way of modeling 3D objects. And what we gain from this geometric construction is filters that can be defined intrinsically of the object, and this equips our deep neural network architecture with invariants to these inelastic deformations that are very important when dealing with non-rigid objects, such as, for example, human body or human faces. So one example of such applications is motion capture that is used in production of movies, but also in virtual and augmented reality applications. And what you see here is technology developed by a Swiss company called PhaseShift that was acquired by Apple several years ago. And now this is what powers the Animoji feature on the iPhone. So the underlying problems here are the problem of analysis, right, or establishing correspondence between the noisy scanned 3D input face and some canonical face object, and the problem of synthesis, where we now try to deform this canonical shape to reproduce the expressions of the input. So we used geometric deep learning architectures like geodesic CNNs on meshes for solving both tasks, both correspondence and synthesis. And actually nowadays we can design hybrid architectures that don't necessarily need to take as input a 3D object, which requires a special sensor. You can take as input a standard 2D input to the image or a video and encode it using a standard CNN, and then decode it using a geometric architecture that produces a mesh. In this case, this was a work of my PhD student, Dominique Colon, that tried to estimate hand shapes and poses from two-dimensional videos. And in collaboration with the British company Ariel AI, we showed a demo of CVPR in 2020, which runs on iPhone 10 times faster than real time, producing these very realistic avatars of humans with detailed faces and hands. And the company was acquired by Snap last year, so you can already see this technology in commercial products of Snap. Now, I see that I'm running out of time, so let me briefly outline a few applications. And I think graphs are probably the most interesting and the most ubiquitous kind of structures, because they allow to model systems of relations and interactions at all scales, from individual molecules to social networks that model the interaction between people at the global scale. And in particular, in social networks, one of the interesting problems is the spread of misinformation, or so-called fake news. And there is empirical evidence that this fake news spread differently on a social network. So using graph neural networks, we tried to learn the spreading patterns of different stories on Twitter. And they were encouraged by results that we got, funding a company called Fabula AI that I created with my PhD students to commercialize this technology. And this company was acquired by Twitter. That's how I ended up there. And I currently have a group that does research on GraphML. And as you can imagine, Twitter has plenty of graphs of different types. This is really one of the key data assets that is used in a lot of different scenarios. Another interesting and prominent kind of applications is in biochemistry, and in particular in drug design. As you know, it is a very expensive and very long business to bring new drugs to the market. So different machine learning methods have been attempted to solve this problem of virtual drug screening, where we start with a humongous space of potentially synthesizable molecules, and we try to narrow it down to only the interesting molecules that will have certain properties, such as efficiency against the pathogen, or maybe solubility, biological availability, and so on. And this gap can be breached by computational methods. And actually, graph neural networks, such as the message passing algorithms, were developed with this application in mind. So if you're familiar with history of graph neural networks, actually, there was a parallel world in computational chemistry and bioinformatics that developed very similar algorithms already in the 90s that tried to solve problems in chemistry, such as classification and screening of molecules. And actually, the Weisfeld-Lehmann algorithm came from problems in chemistry. The earliest work by George Vaduz in the Soviet Union from 1963. He was probably the first one who considered molecules as graphs and used graph computational methods to classify and predict molecular properties. So Weisfeld and Lehmann were inspired by these works. Now, these methods are already probably beyond promising, so they're already being exploited in commercial pipelines by pharma companies. And one recent result from past year was the work of the group of Jim Collins at MIT, where they used graph neural networks to predict new antibiotics. And they discovered that a drug that was initially positioned against diabetes, called halicin, has strong antibiotic properties that can address antibiotic-resistant bacteria. Now, what is also interesting is that traditional small molecule drugs, they try to target protein targets where you typically have these pocket-like structures. So a typical drug binds or attaches itself chemically to a target that is typically a protein molecule, and you see this kind of deep pocket in the molecular surface. What the pharma industry is interested in more recently is what is called PPI, or protein-to-protein interactions, as targets. And unfortunately, in PPI targets, most of the interfaces are flat. So they're typically undruggable by small molecules. And what is possible to try to do is to design biological drugs that are themselves a large biological molecule, such as peptide, protein, or antibody, that bind to these other proteins and disrupt protein interaction. Probably the most famous such mechanism is what is called the program death complex. So it is now used in cancer immunotherapy, and the Nobel Prize in Medicine was awarded for the study of this mechanism 3 years ago. So what we did with collaborators at the PFL, the lab of Bruno Correa, is developing geometric deep learning architecture that we call Massif, that allows to do de novo design, or design from scratch, of new proteins that can bind to these targets. And here you can see examples of 3 synthetically created proteins that bind this oncological target PDL1. These are already designs that are confirmed, their structure is confirmed by X-ray crystallography, so they really work. Now, I'm not saying that this is necessarily immediately translated into a drug, so this will probably take a lot of time. There are many issues that are related to de novo design proteins, such as immunogenicity, but at least as a computational tool, this is quite remarkable. And this was our paper that appeared last year on the cover of Nature Methods. So to wrap up, I should say that a promising direction towards cheaper and faster therapies is what is called drug repositioning, where you don't develop a new drug, but you use approved drugs against new targets, and sometimes they are used in combinations, what is called polypharmacy, and many such drug combinations might have unknown, potentially dangerous side effects. So graph neural networks have been applied by Marinka Zitnik, who is now faculty at Harvard Medical School, to predict drug interactions, in particular side effects. But these interactions can also be positive, so they can be synergistic. And with my colleagues at Imperial College, we are trying to apply these ideas to the domain of nutrition. And as you know, many plant-based food ingredients are rich in compounds that belong to the same chemical class as anti-cancer drugs. And it's not surprising, actually, that many drugs that are used in medicine originally come from the plant kingdom. And this is also prominent in their names. So, for example, even the most trivial thing is aspirin. The chemical name is acetyl salicylic acid. So salicyl comes from the Latin name salice, which is the willow tree. It was extracted in ancient times from the bark of this tree, and people didn't know, of course, about its chemical properties, but they discovered that it has analgesic qualities, and they used it from ancient times. So another example is camptothecin, which is the synthetic analogs of this compound are used in cancer chemotherapy, but it comes from a tree that grows in China that is, again, the Latin name is Camptotheca. So what I'm trying to say is that food is full with these bioactive molecules that are largely unexplored and unknown by experts. They are not tracked by regulators. We have no clue what they do. And if you buy a packaged food in supermarket, you will see a listing of carbohydrates, fats, proteins, vitamins, and microelements. You will not see any content of, let's say, polyphenols, flavonoids, or indoles, right? So this is truly the dark matter of nutrition. And what we try to do is to model the effect of drugs by the way they interact with protein targets. And because proteins interact with each other, we have this, what is called the PPI graph. And by modeling the interaction of drugs or molecules in general with the PPI graph, we can predict whether a certain molecule will have, for example, anti-cancer effects. So we can train a graph neural network classifier on a data set of FDA-approved anti-cancer drugs, and then take a new molecule, for example, that comes from a food ingredient, and pass it through this classifier to predict whether this compound is likely to have anti-cancer effect. Now, of course, this is a huge oversimplification. There are many nuances. And, for example, we need to really understand the different pathways that are involved in the mechanism of these molecules. But long story short, we constructed what we call the food map. So mapping the anti-cancer molecular profiles of over 250 different food ingredients. And we see some prominent champions foods such as tea, citrus, cabbage, celery, that are very rich in different variety of these potential anti-cancer drug-like molecules. And actually, Korean food such as kimchi is based on many of these compounds. So it might be actually a good idea to eat these kind of foods. And of course, completely another dimension is different processing stages, such as, for example, fermentation in case of kimchi, how it affects the molecular content of these anti-cancer drug-like molecules in food. So in this case, you can model the preparation of food or the recipe as a computational graph, where the nodes have different molecular profiles and the edges represent different transformations, such as boiling, frying, etc., that transform differently the different ingredients. But probably the coolest part of this project is that the ingredients that we identified were used by the famous chef Bruno Barbieri. So he directs the Italian Master Chef TV show to cook short recipes for Christmas based on our ingredients. And if you wonder why he's in bed, this was part of the Vodafone Citizen Science campaign. Vodafone funded this project called Dream Lab. So we collaborated with them to use the idle power of smartphones at night to make these computations in a kind of distributed supercomputer. So I think I will stop here on this tasty note. Thank you very much for your attention, and we'll be glad to answer any questions.
Okay, thank you very much for the great talk about the great introduction to the graph neural net and also geometric deep learning, and also for the also like all the different kinds of the applications of these techniques. So let me stop the recording at this moment. And for the audience, if you have any questions, please post on the Zoom chat. Here's like one question in the Zoom chat. Like, would it be better for you to just kind of go through the questions in the chat?
So I'm trying to read them in the chat. I wish to ask your opinion on non-symmetric but scalable alternatives such as VAT. Some might argue that we can just ignore the symmetry of the data by using a simpler model and provide it with enough capacity and data so it can just learn all symmetric configurations. Though seemingly dumb and theoretically unguaranteed, the approach sometimes empirically outperforms symmetric DL as the scale of the data increases. Yeah. So I agree, and this is actually, well, it's probably not a simple, it's not a single answer to this, because this is what happened in computer vision, right? So you need to take into account also how these methods are implemented. So in case of convolutional networks, nobody really says that the translation group is the optimal choice, right? You need to deal, for example, with different, more general deformations and for example, rotations. And yet you have an architecture that is very suitable for the hardware, for the GPU. So because the data was available, you could do just data augmentation. And the work, for example, the first work, the AlexNet architecture from 2012, used data augmentation. So they created new data sampled of transformed and deformed images to compensate for the inability of the architecture to deal with them. So I think that this is a very important consideration, and in some cases, not necessarily the best algorithm is the optimal choice given the architecture, the data, and the problem. Now, of course, what a more principled geometric architectures allow you to do is some kind of built-in guaranteed properties that in many cases might be important. So if you deal with a situation that is data scarce, it would probably be a bad idea to try to use a very generic architecture with a lot of data, because you don't have a lot of data. So when I was a student, there was this maybe a little bit of a maxim that machine learning is the second best choice for solving a problem, and I think it still holds. So if you know everything about your problem, don't use learning. Basically, solve the problem with a handcrafted model. So I think the reasonable trade-off is to model as much as possible, and one way of doing it is by modeling your symmetry structure and then learning something that doesn't fit into the symmetry structure. So here maybe another important comment is that this idealized view of symmetry group, it never really happens in practice. So this is wishful thinking. We don't really have pure translations, right? So think of a video where we have two objects, one moves left, another moves right. So even such simple application, you don't have a global translation group that describes this motion, right? So what you can still say that you have some more general deformation, right, or an automorphism that is close enough to an element of the group. And it was shown by Joan Bruno, for example, that convolutional neural networks are geometrically stable. So if you have, in this sense, they're a little bit similar to multi-scale analysis or wavelets, that if you have something that is approximately a translation, you will get approximate equivariance or approximate invariance. So Fourier transform, for example, doesn't have this property. So this geometric stability is very important. And you can show it for graphs, you can show it for other architectures. And this is actually what makes this architecture work.
Okay. Yeah, maybe I can just read the next question. It is about the NLP. So there have been multiple studies on using GNS in the question answering models. And as you have mentioned in one of the your slides, the transform architecture, which is typically used in this field, can successfully play the role of the GNS. And do you think that the GNS are really necessary in downstream NLP tasks like the QA?
Yeah, it's a good question. So I'm not an expert in NLP, so take this answer with a grain of sand. So people have tried to use graphs to model dependencies in language. The problem that it's difficult to model it by construction. And it probably makes a lot of sense to learn it. So attention is a mechanism of doing it. So probably this is the case where you can have a more general architecture. So you still have permutation invariance, but you have positional encoding that kind of compensates for it. Where graphs seem to be successful is knowledge graphs, or when you incorporate some domain knowledge or some semantic information rather than modeling dependencies in a sentence. So this is more successful. I think graph neural networks have not been particularly successful in replacing transformers, and of course transformers are graph neural networks, as I hope to have convinced you today. So again, it's how much information it makes sense to assume and to inject into the architecture, and in this case, it appears that you probably want to be more generic.
Mm-hmm. And the next question is that I saw several papers regarding the group equivariant neural network, and most of them define specific group structures before actually seeing the data, and hope the symmetry assumed by the architectures well describe the data. And is it possible to learn the proper group, the structures in a data-driven way? For instance, I can imagine setting like group representations as parameters to be learned, and fit the model and hope the model discovers the proper symmetry structure solely from the data. And if that would be too hard, what sort of the inductive biases should we give to the model?
Yeah, excellent question. So maybe one thing is some kind of overarching limitation is that we somehow implicitly need to assume that the group is tractable, right? So when it's a finite group, then it has to be sufficiently small. The permutations, for example, are too big, right? That's why, for example, in graphs, we cannot do the same thing that we did with, for example, with homogeneous spaces or with grids. We cannot keep all the possible permutations because there will be n factorial such. When the group is continuous, we need to assume that it's sufficiently of low dimension, right? So having said that, of course, you can assume a more general group and then see whether you can restrict it. The problem that it's somewhat ambiguous, and it's a trade-off. So imagine that you have again think of a problem from computer vision. So imagine that you have objects that move mostly horizontally, but also a little bit vertically, right? So in this case, you can assume that either a two-dimensional translation group, right, and it will describe all the possible motions, or you can assume that the main, let's say, the principal degree of freedom is only one-dimensional horizontal translation, and the vertical translations will be absorbed into this geometric stability, or you can treat them with data augmentation. So it depends what makes more sense, right? So there is no single recipe for doing it, and I should say that this question of how to learn the symmetry from the data is still open. I have not seen many works doing it, so this is probably one of the next steps in geometric deep learning.
Yeah, it was a very interesting question. There's also one more question about chemistry, actually. Although the ideas of the geometric deep learning show the state-of-the-art results in the biochemical tests, still the black box issue of the deep learning prevents the practitioner from applying the deep learning in the real world. So may I ask you about the idea of like model the interpretability of the geometric deep learning related to the drug design?
Yeah, good question. So again, take it with a grain of salt. I'm not a chemist, so I've been working with some chemists that probably have much better understanding of this field. But my interpretation is that chemists don't think of molecules as graphs. So, right. So it's of course a convenient abstraction, but chemists think of them as structures. So you think of, I don't know, aromatic ring, for example, and here, I don't know, amino group or something like this. So it's not just nodes and edges. So in this case, it seems to me that we need to go beyond the traditional message passing paradigm. Well, still use some form of message passing, but that is a way of higher order structures. So in particular, we want to say that a ring is a ring, right? So it is a special object. So it's not, we don't just have nodes and edges in a graph, we also have cells. So it's a cell complex. And for example, we want to be able to pass messages. So we don't want to send information along the ring, along the edges of the ring. We want to have a single object that is called the ring, and we basically we can do special form of message passing for it. So this was our recent line of works with the group of Pietro Leo in Cambridge, where we show two types of architecture, what we call simplicial message passing and cellular message passing. So it is again motivated by problems in chemistry. We show significantly better results. They're also more interpretable because in this case, you have the actual structures that are chemically meaningful that you do. Now, having said that, of course, deep learning is a black box or at least a gray box. So there are methods of attribution, for example, that you can see what kind of structures are responsible for certain classification of prediction of certain molecular properties. So my PhD student Federico Monti had this paper in PNAS about attribution methods for graph neural networks for chemistry, together with collaborators at Google. Yeah, but it's still to a large extent an open problem. So another interesting thing is that now there is this trend of equivariant message passing. So a graph neural network that assumes additional structure. And this is actually an important problem that I maybe only briefly mentioned. So the symmetry of the domain is distinct from symmetry of the data. So in physics, I think this is called external and internal symmetry. So the external symmetry is the symmetry of the space-time, and the internal symmetry is the symmetry of the field. So the same analogy, you can think of an RGB image, right? That the structure of the domain, for example, in the domain you might have a translation group, but the symmetry of the image itself, of the data, can be, for example, permutation at every pixel of the RGB channels, right? Of course, maybe it's a made-up problem. Nobody in his sane mind would permute at each pixel differently the RGB channels, but you can see that this is a very different structure. So the general model for this in what Taco Cohen has done in his PhD thesis is vector bundles. Now, in chemistry in particular, why this is important? Because molecules are not just any abstract graphs, these are geometric graphs. So they live in three-dimensional space. And some properties, such as, for example, atomic numbers and charges and so on, are abstract features, but some other properties, such as, for example, geometric coordinates of the atoms, are geometric features. So, for example, if I want to predict the atomization energy of a molecule, I don't care how it's located in the space, right? So I want to have some aggregation process, message passing process that is equivariant under, for example, the Euclidean group for these particular subset of features. So there are several recent works that try to do it. And again, this is more interpretable because you don't just treat the different features in the same way. You treat them as they should be treated as the different kind of features. Yeah. So again, maybe a little bit long and cumbersome answer, but I think the shorter answer is that there are several directions in this field, but probably not fully satisfactory.
Actually, I also like some follow-up questions about the drop design things. Actually, because most of the architectures, sorry, you mentioned was kind of the techniques that can basically process the graph data. But I was wondering, like basically in the kind of drop design case, I was thinking that we might some kind of techniques that can not only kind of process the data, but also can kind of like generate some graph structures. So like we are basically seeing the huge success of the GAN in the image space. So we can think of like making some sort of the GAN for the graphs as well. But I guess like making the GAN for the graph data might be like quite challenging in terms of that the graph basically can combine some continuous data and the discrete data. Basically, some features that are designed for the nodes and the edges might be some continuous data, but some kind of the connectivity information might be some discrete data. So basically, generating some this kind of the information that is kind of mixing some continuous and the discrete things might be kind of challenging in terms of making some GAN sort of the architecture. So do you have any kind of thoughts about how we can make some sort of the generative models for the graphs?
Yeah, so, well, it's an excellent question. So generating graphs is also one of the big challenges. And one of the reasons, if you think of images, generating images is very easy, at least in principle, right? Because you have a global representation. So the typical autoencoder type networks, they would input an image, right? And code it to some latent factor and then decode the latent factor into another image. And you can look at the reconstruction loss, right? So you can compare the input to the output and just take the difference and the norm and say that I'm far or I'm close to my input, right? Now try to do it with a graph. So you don't have a canonical ordering of the nodes. So a network will take a graph, encode it into something, decode another graph, and now tell whether they're similar or not, right? So there are certain architectures that construct the graph progressively, right? So there are maybe for particular kind of problems, like in chemistry, you can say that instead of a graph, I decompose the graph into a junction tree of structures. So this was the junction tree variation autoencoders of Tomi Yakola from I think 2018. This is actually what is used for building molecules. So it really depends on what kind of graphs you assume. In molecules, you build them in a certain way. Maybe some other graphs you build them in another way. So I think there is no quick answer, but I think maybe the quick answer is that this is way more complex than generating images.
Actually, there's one more question in the Zoom chat. So neural nets have successfully shown to learn some fundamental properties like the gauge symmetries, invariants, equivalence, and the fundamental physics. And I wonder what is the main contribution to this, like maybe the nature of the given data set or the given biases inside the models or something else.
Right. So standard, well, when you probably say neural nets, probably you mean something that looks like a perceptron, right? So there are universal approximators. Now, convolutional neural networks are also universal approximators for translation equivalent functions. So basically, you restrict your class of functions. So you introduce additional inductive bias. So you introduce extra regularity. So nobody actually uses perceptrons. So it's not correct to say that perceptrons have no inductive bias, because you usually use them the way that you train them. So the regularization already imposes certain inductive bias. So regularization such as weight decay or dropout, or even some optimization algorithms restrict you to a certain class of regularity, such as Sobolev and so on. And so this is the only way to deal with the curse of dimensionality. And assuming geometric priors, right? So geometric regularity is a stronger way of dealing with the curse of dimensionality. Of course, it requires you to assume something about your problem. So in some cases, right? So if you deal with images, it makes a lot of sense to assume, for example, translation invariance, right? Or maybe translation and rotation. If you have some general high-dimensional data, maybe the only thing that you want to assume is that you have some low-dimensional intrinsic structure, like in manifold learning. So in this case, you probably will be learning some nearest neighbor graph, or maybe some more interesting topological structure. So topological data analysis in the same vein is coming back with deep learning, and now with interesting results. So yeah, so inductive bias, I think in some cases you can assume certain things a priori. In some cases you can learn it from the data, but I think there is no clear single recipe.
Yeah, I have some couple of the questions, especially for the applications that you have shown in these slides. Basically, I was quite impressed that you are kind of handling very different types of the graph data, like some graph data which is coming from the social network service, like the Twitter, and also some graph data that are used in the drug designs. But I thought that basically, these kind of the graph data might have some very different types in terms of that. The graph coming from the social network might be one giant kind of the graph structure. And for the graphs that we are using for the drug design might be like having lots of these small kind of scale of the graphs. So in terms of like having these two very different types of the graphs data, like, having like one very big graph or just having like lots of these small graphs, obviously you can just apply the same kind of the graph neural net techniques, but there might be some aspects that we might need to consider to deal with these kind of two very different types of the data. So do you have any kind of the comments for like handling these two cases?
Yeah, so I think this is what is nice about GraphML, that the space of problems is very diverse. So what you mentioned, well, roughly speaking, there are three classes of problems, right? So it's node classification or regression, right? It's graph classification or regression, or it's a link prediction, which typically you see in recommender systems. So in social networks, one of the challenges, for example, is at the large scale. So for example, if you think of Twitter or Facebook graphs, they normally have hundreds of millions of nodes and billions of edges. So computational efficiency and large scale is one challenge. In case of molecules, for example, these are relatively simple small graphs, but they have a lot more structure. So you want probably your architecture to be adapted to these particular structures. So another challenge is, for example, that we are probably spoiled by using GPUs, right? And this is a kind of a hammer that is used for every nail, but some of the nails are screws, and graphs are screws from this perspective for the GPU hammer. So you probably want some new kind of architecture that is more suitable for this kind of data. And I know that several semiconductor companies are trying to develop a new generation of architectures that will go beyond, let's say, this well-structured grid-like data. So one of them is a British startup called GraphCore. Graph is already in the name of the company. So they're building these somewhat exotic but very powerful architectures for these cases. So I don't think that there is really some generic comment or advice to say. It really depends on the application. So what is good that now there is also a set of standardized benchmarks, the Open Graph benchmark that considers problems from these different domains. I should say that also, so in graphs, basically you have three kinds of things, right? So you have the graph structure itself, right? So the topology, you have the data on the graph, and you also have the task. And the architectural choice depends on all three things. So let me give you an example. So the typical example that you assume in most graph neural networks is homophily. It means that the data is structured in such a way that my neighbors are similar to me, right? Now, you also have problems of bottlenecks. So if you have, for example, the structure of the graph is such that the number of neighbors grows very fast. This is the case of scale-free networks such as social networks, right? Where we have this small world phenomenon with a small number of degrees of separation. And also the task depends on long-range interactions. So if to make a decision about a node, I need to query nodes that are a few hops away. Then I need to squeeze a lot of information, a lot of features from these nodes to a single feature vector, and this creates a bottleneck, so what is called oversquashing. That's why actually some of the rewiring algorithms that I mentioned were built exactly for these kind of situations. So you see that it's both the task, whether the task depends on the long-term dependencies, whether it's the structure of the graph or have exponential growth of the neighbors, and the kind of data, whether the data is homophilic or heterophilic, they all determine what kind of architecture you should be using. So it's not, I can have exactly the same graph, exactly the same data, but different task, and I will use maybe a different architecture. So it's hard to say a priori. And it's not well understood theoretically, so I think there is a lot to do.
Actually, also in terms of the structure of the graphs, actually, I also was thinking that there might be also kind of some special types of like some structure of the graphs. So you show some cases like just having very general graphs and also having the grids, which might be kind of the special, the kinds of the graph. And also you show the case of having the manifold as the graph structure. But I thought that there might be also some other types of some special structure of the graph, like for for example, if we have the planar graphs, then we are basically having some sort of the order information in terms of that we can somehow define the orientations of the nodes, but it's not exactly defining the case of the manifold, like having some sort of the surfaces where basically triangles where the tetrahedrons, like some simplex is there, but still we are having some orientations. Where I guess there might also some cases that we have the hypergraphs, which is basically not just connecting two nodes, but connecting multiple nodes. But so basically, when you have this kind of some more like some special structures on the graphs, there'd be some ways that we can somehow leverage this kind of some extra information in this in the processing.
Right, excellent question. So let's take all this way, let's say from a grid, right? So in a grid, as you said, let's think of two-dimensional grid. So two-dimensional grid is a tensor product of one-dimensional grids. That's why you have this ordering. That's why you have orientation. For example, on the other extremity, you have a general graph where you have arbitrary ordering of the nodes, right? So your ambiguity is permutation, right? Local permutation. So your filters are necessarily isotropic, so you don't have a notion of direction. So on a grid, you have a perfect global notion of direction, right? Because of this tensor product structure. On a general graph, you don't have any notion of direction, right? So meshes and are kind of halfway between them because you still have ambiguity, but this ambiguity is more restricted. So instead of a permutation, you have rotation, right? So I can basically, I don't know how to order my neighbor nodes, but I can pick one of them, and all the rest now are ordered in, for example, clockwise orientation, right? Because this is we have extra structure, right? So this is locally Euclidean space. So in which cases you can infuse this information is a good question. So on general graphs, what we show, for example, when you treat you can treat a graph as a simplicial complex, right? So it is a hypergraph, but a more disciplined one where we have more structure. So it's not just any collection of edges, right? That form nodes that forms a hyper edge, but they have certain embedding hierarchy. And same thing with cellular complexes. So in this case, you can actually you can upgrade your message passing to take into account these structures in a disciplined way. Now, hypergraphs are interesting because, as you said, many kinds of interactions are not pairwise. So you can think of even cases of social networks. You might come up with interactions that are not necessarily between two nodes, but between multiple nodes. There are some attempts to extend message passing architectures to hypergraphs, but this is still very early and emerging trend. So it's it's work in progress.
Thanks. I guess we can take the last question, the Zoom chat. When generating a graph from a symmetric learning view, a principled and proper way would be jointly sampling n nodes, passing them through the equivariant net, and decoding the edge pairs. That this incurs like quadratic cost because we don't know which edges to pass the messages through. So this enforces many methods like the graph neural net, the graph RNN to rely on the autoregressive the addition of the nodes, which imposes a ordering of the own nodes for T-shirt forcing and the break symmetry. So would there be ways bypass such kind of dilemma? I wonder how this problem is being solved in the current chemical AI domain.
Yeah. So again, I don't think that I have a satisfactory answer to this, but let me describe some direction on which we are working now. And the first paper in this series appeared at ICML this year. So one thing that sorry that I started a little bit from far away. I hope to get to the point of the question. So one thing that disturbs me in this geometric deep learning field is that for structures such as manifolds or grids, you always have a continuous counterpart, right? So a grid, you can think of it as a certain discretization of the plane, for example, right? For a mesh, you can think of a discretization of a surface, right? Or a manifold. A graph is inherently discrete, right? Which is disturbing. You don't have a continuous version of the graph. So there is an entire field that is called network geometry that tries for certain kinds of graphs, such as scale-free networks. You can think of them as sampling of some space that has non-Euclidean structures, so in particular hyperbolic space. And if you can do it, so if I give you a graph and you can think of it as nearest neighbor graph in some continuous space, let's say in a Poincare disk or some other model of hyperbolic space, then getting rid of the graph is a very powerful concept, because you can think of a graph as just a convenience, a way of representing, for example, spatial derivatives. So what we try to do in the paper that I mentioned is to think of graph neural networks as a form of diffusion equations. Same way as you have neural ODEs, right? That model residual networks as a particular discretization of an earlier scheme for a certain differential equation, an ODE that evolves the feature vectors. Here we can think of a PDE, a partial differential equation, a diffusion equation that diffuses information in some space in a nonlinear way. So you can think of a graph attention network. So the attention can be interpreted as nonlinear diffusivity function that diffuses your information, right? Your features at different speed at different points in the space, right? That also evolves together. It depends on the features. And this way we can think of a standard GATT type architectures or more general graph neural networks as a particular discretization that is not necessarily the best for this diffusion PDE. So the temporal part is discretized by basically the layers of a graph neural network are steps, temporal steps of your solver. The interesting part is the spatial derivatives. So the different discretization of the space actually amount to the graph rewiring. And what we also show in a follow-up paper that's still unpublished is if you think of a graph as its instantiation in this continuous space, you can actually evolve the graph, right, or the points of the nodes, the positional coordinates of the nodes during this evolution, during this diffusion equation. So this is a nonlinear diffusion equation that in differential geometry is called the Beltrami flow. It has been used for image processing about 20 years ago. So this is our take on positional encoding. So people ask, what is the right way of positional encoding of the graph? Whether you should use, for example, the eigenvectors of the Laplacian, or whether you should use some structural encoding. So here we're saying that it's specific for the task. So we evolve the positional encoding of the graph, and actually the positional encoding is the graph. It replaces the graph. And it is evolved, it is optimized for the downstream task. So if you solve one kind of task, maybe your positional encoding, right, or your graph will be different. So it's graph rewiring and positional encoding in a single take. So and this way, basically, you also have efficient ways of dealing with this quadratic complexity, right? Because you don't need to pass information from everywhere to everywhere. You can make it local. So the physical analogy would be something like fast multiple methods that actually use the principle of scale separation. That from certain distances you can consider distant nodes as a single one, right? So you can agglomerate them and do this kind of hierarchical information propagation. Yeah. So this is maybe again a bit long and convoluted answer, but. Yeah, so there are some ways, and this is just one way of dealing with this quadratic complexity.
Yeah, that sounds quite interesting. Idea of like generating the graphs without having the n-squared the complexity. Actually, yeah, it's time to wrap up, but can I ask like a quick question? Like that might be the last question. So you were kind of working on the project called the CETI, which was kind of aiming at kind of learning some, like understanding the communications with sperm whales. So I was kind of curious, like how your research is kind of related to like understanding the communications with sperm whales.
Yeah, well, so this is a crazy project, and I would say very ambitious, and it's a big collaboration with a lot of people involved on the biology side, on the robotics side. So I'm in charge of the machine learning. It's not related to geometric deep learning, or even though you can think of the data set that we are trying to build as a kind of Twitter of whales, or a social network where we try to understand who speaks to whom and how different whales are related. But I can talk about whales for probably for another hour. It's really fascinating topic, but maybe very briefly. So they communicate with broadband clicks. So it's clicks that have a different temporal structure. So they're actually very powerful. This is the loudest sound that an animal produces on Earth, at least among known animals. they use these clicks for echolocation. They can use them for stunning prey. So it is so powerful that you can kill a fish literally with this sound. And they also use these clicks for communication. So what we're trying to do, first of all, collect large data sets or building specific hardware that will be both attached to the whales, so special tags that will be recording their communication, as well as listening sensor arrays in Dominica, that will, where there is a large resident population of sperm whales. And we try to, first of all, use NLP-like methods to understand structure. So what are the basic building blocks, like phonemes in human languages, how they're combined, maybe used as morphemes. So basically, what is the grammar that creates this communication? And then, of course, the most challenging part is semantics. So we need to find relations between certain communication and behaviors. And our hope is that the next step would be, if we have a sufficiently good language model for sperm whale communication, we'll have a kind of interactive chatbot that will be playing back the signals based on the specific context of responding to the whales. And by recording their responses, hopefully we'll be able to get a better understanding of what they're saying. But I should say that even discovering some language-like structures would be a huge breakthrough, because so far it is not known whether they have any language at all, or something that looks like a language.
Yeah, that sounds quite interesting, that the NLP techniques can be also used to understand the whales' languages. Yeah, I think we need to wrap up now. So thank you very much for Michael again for giving the great talk, especially in the early morning in London. It was really impressive talk. And yeah, so we're gonna continue this colloquium, but we're gonna have the break for next week because we have the holidays. So we're gonna continue for the week after the next week. So thank you again, Michael. And we'll see. We'll meet again in 2 weeks. Okay. Thank you
very much.
Thank you very much, Michael. Yeah, I would be happy if I can just meet sometime in the future after this COVID pandemic in some of the conferences. Yeah.
Yep. So there was a question about the paper. So yeah, I will probably send me an email and I will send the link.
Yeah. I will forward that email to the people. Okay. Yeah. Thank you very much. Thank you.
Thank you. Goodbye.
Bye.